This video tutorial is going to discuss and illustrate a basic workflow for well performance analysis and modeling in the Eagle Ford, specifically for deep gas condensate wells. So here's an example that we have with about a year and a half worth of production data. We've got gas production rates shown here in red, our CGR condensate gas ratio shown in green, and tubing pressures in blue, calculated to bottom hole pressures shown here using a multi-phase pressure loss correlation. So that's our raw data. What I'd like to do now is take a look at some of the inputs for this file. What you'll notice is that we have very, very high pressure, high temperature. So this is common in the deep part of the Eagle Ford. And it's something that we're going to have to take some specific considerations when we're modeling. So very high pressure, high temperature environment. One of the things that we're going to want to look at right away are the geomechanical effects that go along with that high pressure, high temperature environment. So we're going to enable a gamma factor in the Yilmaz and Nur correlation for pressure dependent permeability of 2e to the minus 4. This will be our minimum or default pressure dependent permeability condition. There's good evidence to suggest that this is a very reasonable minimum expectation for geomechanical effects in such a high pressure temperature location. So we'll keep that in our minds as we go through. Now for petrophysical properties, we've got about a 200-foot net pay thickness. As you're going to see later, though, there's some uncertainty in this number, so we're going to explore different, potentially different options for total fracture height connectivity to the formation. And then we have also entered our porosity and saturations. Other number that's going to be of importance is formation compressibility. Again, in a high pressure, high temperature environment like this, we're going to tend to use a higher nominal value for formation compressibility than, let's say, the Hall correlation, which is somewhat less. So we're using a value of 10 microsips for this case as a starting position. And we'll explore even higher, the results for looking at even higher formation compressibilities when we do some probabilistic and sensitivity analysis later on. Other number that we want to pay attention to here is the condensate gas ratio. These are all our gas properties. We're going to need to put a number in here. So let's go back to the diagnostics and take a look. As you can see, the condensate gas ratio is slightly declining, but relatively constant throughout the history of the production. We're starting off at about, on average, about 345, 350 barrels per million. There's a little bit of a decrease, comes back up, and all in all it trends downwards to close to 300 at the end, but by no means a significant drop in CGR. So we're going to model that as a CGR of 345. And so we want to actually match that number to as close to the initial conditions that we think we have as possible. Now, what you want to note for this example is we have no laboratory PBT analysis. So we're really going on the field data to get a sense for what the liquid yield in this system is, which is not a bad way to do things because the field data we have much more time averaging that we can go by and get a real sense for how much liquids are making it up to the surface. Okay, now in terms of the properties that are being exposed here, we've chosen a gas type of liquids-rich gas. That's in comparison to just wet gas or dry gas. For the vaporized oil ratio correlation, we've chosen constant RV. This is the simplest scenario. In this scenario, basically we're just doing analytical modeling, and we're saying that there is no condensate dropout in the reservoir. What we can do, however, is accommodate condensate dropout later on in the production forecast. This is a very reasonable option to use in this case, particularly because we really don't see much evidence of condensate dropout in the production history. However, we may want to account for potential condensate dropping out later on as we do a long-term production forecast. So we're going to use those options for our analysis. And so let's go ahead and start taking a look at some basic diagnostics for the data. Again, here's our data chart. Shows our condensate rates, gas production rates, water. There is some water production. Fairly noisy. This is clearly in the early life here we have some fracture fluid flow back, and then we have some sort of base water rates that are fairly low in the production history of the well. Again, our CGR diagnostic is shown here. I can expand the view a little bit. Shows a slight decline in condensate gas ratio. That's fairly consistent with the decline in bottom hole flowing pressures. That's something that would be expected. We would expect the amount of condensates that make it to surface would be more under higher flowing pressure conditions when we're not dropping as much condensate out in the wellbore or in the formation. Let's go ahead and do an analysis on this well. I'm going to start with the unconventional reservoir superposition time analysis. This is really the best approach for looking at these tight fractured gas wells, particularly for gas condensate. This will give us a good sense, A, for flow regime identification, and B, will allow us to extrapolate some bulk reservoir characteristics, such as A square root K, which is the slope of this line, the estimate of the dimensionless fracture connectivity, which is the y-intercept, and the total connected pore volume, which is the extrapolation of the flowing material balance. Before we get this thing started, I've done some basic filtering on this data to remove some of the outliers. I'm just going to hide those so that we can't see them. And we're going to get started with this. So let's move. I usually start by moving the red dot into the origin, and then we can just kind of dial that into position. Now, one thing that, again, we want to remind ourselves is that there will be some basic geomechanical effects happening here. So what you're looking at right now is a square root of time response that has significant upward concavity. We're going to want to turn the geomechanical term on, and you can see what effect that has on the data. That actually reduces the amount of upward concavity and tries to linearize the production response back to something that would be more consistent with a constant permeability system. So we're going to start by doing that right away, because we believe that in such a high pressure, high temperature environment, there's very likely going to be some geomechanical effects, pressure dependent permeability effects. So let's dial that line back down. We're going to try and match it through the early data as best we can. And what we're really looking for is the point at which the data departs from the straight line behavior. That is our time to end of linear flow response. Let me move that scale down a little bit, and we're going to move the dotted vertical line over to try and pick out where that occurs. Now, it's a little bit difficult to see where that occurs on this line. It's somewhat subjective. So we're going to use the flowing material balance to help us characterize that. And the flowing material balance will actually do a really nice job of helping us dial in what that time to end of linear flow point is. And these two interpretations are now consistent with each other. So we have something that's in the vicinity of 25 acres. And we can continue to sort of fine tune that to get it to a position that makes sense. It doesn't have to be exact at this point. This is more of a rough analysis that will give us a sense of just the bulk parameters. What we're going to do as part of the next step is load these results into the analytical model to fine-tune them in a physical reservoir model that has fractures and different regions of permeability and drainage volumes. Okay, so before we go any further, we want to enter in some basic reservoir completion parameters. LE is going to be 5,500 feet. That's our effective horizontal well length based on the top of the first stage to the end of the last stage. Number of fractures in this case, this is a plug-in perf completion. The number of stages is 20, and we have 4 perf clusters per stage. So we have a total of 80 perforation clusters in this well. What we normally do is assume some sort of perf cluster efficiency, and we're going to assume 50% perf cluster efficiency in this case. And that gives us a matrix permeability of about 450 nanodarcies, and it gives us a fracture length of 100 feet. So this is going to be our base model that we're going to work with to get started. But before we move on from here, let's just take a look at the post-transition B value. As we can see on the type curve, the model is not matching the post-transition behavior. So a b-value of 0.5 obviously is not sufficient to match this performance. So let's ramp that up to 1. Even a hyperbolic decline isn't matching that performance. So if we ramp that all the way up to, say, 1.4 or 1.5 even, we can see now that we're starting to get a good match of that data. So clearly there's some strong pressure support going on in the late life of this well after the transition. If it were just pure volumetric depletion, we would expect a b-value of 1 or less. And we can see the b-value is actually in excess of 1, or in excess of harmonic. Not quite up to the linear flow level, so there is still some transition. But we are seeing some definitive pressure support happening here. Our estimate of original gas in place is close to 4 BCF. Again, keep in mind that 4 BCF is just the stimulated reservoir volume. It doesn't include what might be contributing from the outside. So let's go forward from here. We've got a good place to get some seed parameters for our model. We're going to go and create an analytical model. So we'll go to gas, horizontal multifrac, and we're going to choose the enhanced frac region model. That is the standard analytical model that we use for all shale gas reservoirs. Eagle Ford is no exception. So we're going to choose that enhanced frac region model. We're going to seed it with the reservoir parameters, and we're going to seed it with our results from the unconventional reservoir superposition plot. Let's change the name of this analysis just so we have something that's a little more intuitive. We're going to call this linear flow analysis. Okay, so that gives us our basic linear flow properties from the straight line, gives us a sense for the size of the stimulated reservoir volume, and also gives us that additional information that we do expect to see some pressure support from beyond the fracture tips. Okay, so now we've got a base model here. The only thing that didn't come in is FCD. I'm going to just seed that with 500. That's a good place to start. That's sort of a maximum FCD that we would expect to see. XI is another one that doesn't come in from the basic analysis. We're going to start by assuming that XI is equal to the fracture spacing. XI is defined as the distance to the permeability boundary, or the transition to lower permeability from the fracture face. And if we assume that's equal to the spacing, then basically there's only one permeability in between those fractures. So let's take a look at our result. As you can see, we've got a very nice match of the simulated data against the actual production response. We're going to want to try and fine-tune that a little bit to capture the end bit. We can do that by giving this model a little bit more flexibility. In this case, we can allow permeability, the outer permeability, or the permeability 2 to change, and we can allow the XI region to adjust as well. So I'm marking those as automatically calculated variables for the APE routine that we're going to run in a minute. We'll do the same thing for FCD, but I'm going to put an upper limit on FCD to make sure that it doesn't go above 500. We'll keep that as the upper limit. And in addition, this gamma value is also an unknown. We're using some sort of a minimum value for gamma here. I'm going to put that on auto, and I'm also going to specify that its value can't go below 2e to the minus 4. So we're going to call that one the minimum. It can go up as high as it needs to go. We'll also allow K1 to be a flexible matching parameter. Now, just to get this thing going, I'm going to drop K2 down a little bit. And so let's make this, say, 5e to the minus 5. Okay, now that's not going to change anything until I also change xi. So let's drop xi down to 45. And okay, we've dropped the solution down a little bit. That should be hopefully enough to get us close and get us started. So I'm going to start the automatic parameter estimation routine, allow the model to make its own adjustments to get the best match of the simulated production response and the actual pressures that we have measured here. Okay, so you can see it's come up with a decent history match. We're a little bit shy on the history match at the bottom here. What I might try and do is just provide some extra weighting to these points. Because these points are at the beginning of the forecast, it's probably a good idea that we try and get the simulated model to come down and match those points a bit better. So let's see if we can pull it down and have it match those last points with a little bit more accuracy. And you can see it's doing a fine job of accommodating all the data that we have. Okay, so we'll stop that there. And we're getting pretty close. If we really want to be detail oriented about this, we can put some more weighting here and here and just see if we can get that solution to conform a little bit better to the data. Okay, so we'll stop it there. All right, so now we're ready to do a production forecast. Let's just quickly take a look at the APE error. We've got about 15%. That's not too bad. We'll go to the forecast and test design. I'm going to do a production forecast for 600 months. And we're going to allow the pressure to drop down over time to 1,000 psi. 1,000 psi is a good minimum pressure for a reservoir that has an initial pressure of around 10,000 or 11,000 psi. That's 10% of the initial pressure, so it's reasonable to expect that over the long term, we can bring the bottom hole pressure down to something close to that value. Now for the CGR, at the end of the production data, if you recall, our CGR has dropped. It's down to about, on average, let's say 270. So we want our starting CGR to be 270. And we're going to allow the final CGR to ramp down to whatever value we want it to. Now let's keep it at 270 for now. So this is the optimistic case, which suggests that CGR is going to stay flat at 270. But we can try some different cases where we allow CGR to change to whatever value we think is reasonable. Okay, so that's going to be our forecast. Our EUR for this case is coming up to be around 2 BCF, it looks like. All right, so let me right-click on this. I'm going to call this case the minimum case. Okay, and we're calling it minimum because we have a minimum drainage volume and a minimum fracture size. I'm going to create another case here. And in this case, we're going to explore larger reservoir sizes. So we'll rename this one in a minute. Let's start by seeding it with all of the input reservoir parameters from the minimum case. And so our history match here should be identical to the previous one, and it is. But what we're going to do now is we're going to recognize the fact that the actual well spacing is not 200 feet, but rather 1,200 feet. So we have access to more reservoir on the outside of the fracture tips. This is a very reasonable assumption, both because we know what the well spacing is. We know that there is resource out here beyond the fracture tips that's accessible to this well. And also because if we go back to our linear flow analysis, there is very strong evidence to suggest that we do have pressure support. So the B value of 1.5 suggests that we're not just depleting an SRV, but that we're also drawing in gas from outside beyond the fracture tips. This is very strong evidence to support the idea of using a larger reservoir here. So let's rename this, and I'm going to call this case case 1. Okay, so case 1 will simply be one potential option where we've got a large drainage area. And in fact, from this point on, we're not going to change the drainage area. We're going to leave that as a constant, but what we are going to change are other parameters such as fracture length. So let me rematch this case. And again, I'm going to set the minimum value for gamma to 2e to the minus 4. And we'll accept that. We're going to set the maximum FCD to 500. And we're going to put all of these things on auto, with the exception of frac length, and allow this to converge and try and get a good match of the data. Okay, so as you can see, we're getting a very good match of the data in this case. In fact, it's better than our minimum match. And I'm just going to shut that off because I think it's good enough the way it is. Our APE history match error here is down to 5%, so it's actually even a better match of the data. We've got a K2 of about 50. Let's change the units here to nanodarcies. Change both sets of units to nanodarcies. So we've got 57 nanodarcies. Let me go back to my minimum case and see what we have there. Actually very similar for K2, which is good. We're getting consistency in our K2. We're in the anywhere from 40 to 50 nanodarcies for our matrix permeability. Let's create a production forecast for this case. So again, we've got 600 months. We're going to allow the pressure to ramp down to 1,000. And we're going to give it the option of, at some point, let's change, I can't remember what we used here. We used 270. So we're going to give ourselves the option to change that from 270, maybe to some other value later on. And now our EUR is 3480. So we have a better EUR for this example, which of course makes sense because we're providing more access to more reservoir. We haven't closed it off in terms of just an SRV model. We've added more reservoir on the outside. So let's compare those two cases on a decline plot. There's our case 1, and there's our minimum case. Okay, so case 1 obviously gives us access to greater reserves, gives us greater recovery in the long term. Now let's create another example. We're going to do one more, and the only thing I'm going to change in this one is I just want to illustrate the fact that the solution for the history match is, or the uniqueness of the history match is questionable because we'll be able to have just as good of a match using a larger frac length. Okay, so we're going to start by bringing in the case 1 parameters, but in this case, instead of using just 100 feet, I'm going to go to a maximum frac length, and we'll choose 400. That's a reasonable maximum. Most people wouldn't believe that the effective frac length in this sort of completion could exceed 400. There's a chance that it could, but it's very unlikely. So now, of course, our history match is way up here. To bring it back down to the data, we're going to need to lower all of these numbers. So I'm going to start by lowering the FCD. Let's bring that down to 50. Let's bring the K1 down to, let's try 0.0001. And I'm just trying to get the solution a little bit closer. We'll bring this one down to, let's say 1 e to the minus 5. That's 10 nanodarcies. So let's change these guys into nanos. You can have better success reading them. Our XI, let's bring that one down as well. I'll bring that down to 25, maybe even lower, 15. And we can start to see we're getting close to a match here as well. Again, I'm going to put the same limits on here, so this has to be higher than 2 e to the minus 4. We're going to force FCD to remain above or below 500. Accept that. Put these guys all on auto. And see if we can get this a little bit closer in terms of its match as well. Again, what we're constraining here is our fracture length, and we're allowing everything to automatically estimate around that fracture length. And as you can see, we're getting a very good match of this data as well with these assumptions. So that's probably good like that. I'll stop it there. We'll take a look at the APE error. For this one, it's 10%. That's pretty decent. Let's go to our forecast and test design. Again, same thing, we'll do 600 months. We're going to ramp that down to 1,000. And we're going to allow that to ramp also, set that to 270 as a starting point, and keep it at 270 for now. All right, let's plot this one on the EUR plot as well. Okay, and as expected, our larger fracs give us the most optimistic forecast. So we're ranging anywhere from about 2 BCF if we take the minimum case, which is really, I'd call it more like a P99, because it doesn't give any expected value to anything beyond the end of the fracture tips, which in this case are only 100 feet. So it's very pessimistic. We have our case with minimum frac length, which is about 3.5 BCF, and then we have our high side case with larger fractures, which is approaching 5 BCF. So a decent range that we've deterministically explored here with these 3 examples. And I'll set the name to this one to be case 2. So our case 2 was large fracs. Our case 1 was small fracs. So our small frac case, our large frac case. Now what I've just shown you here is an example of deterministic range modeling. So we're looking at keeping all the other parameters similar and just changing one thing. Or maybe a better way to say it is we're going to change just one thing and anchor on that one thing. So we never adjusted the fracture length. We left it at 400, specified it, but allowed everything to auto estimate around it to get the best history match. And as we could see, in every case, we were able to get a history match that was just as good, but it gave us a different production forecast. So keep in mind, we've only done this for fracture length. There are also other parameters that have uncertainty. For example, H. The H that we're using is an estimate from an offset log in a pilot well, open hole vertical log, where we've estimated 200 feet. But the true fracture height could be less or it could be more than that. So we need to investigate uncertainty in this number as well. In addition, our porosity has some uncertainty surrounding it. Our gamma factor has uncertainty surrounding it. And as I mentioned at the beginning of the discussion, our formation compressibility also has uncertainty around it. So rather than generate all of these deterministic cases and fill up a whole file with a multitude of these cases, we're going to take this into our risk and sensitivity analysis, which is a probabilistic approach for modeling and forecasting. And in this module, we can account for all of those uncertainties and do a Monte Carlo simulation where we can run 100 or 200 or 300 cases and incorporate the full description of the variance in the parameter space and get all of that done in one run. And so it makes things a little bit more efficient than trying to investigate all of these non-uniqueness, potential non-uniqueness factors with a one-off model, with a series of one-off models. So what I'm going to do is we'll use case 1 as our base model to do this. So let's just go ahead and delete case 2 and just use case 1. And I'm going to rename case 1 to be the base case. Base case suggesting that we're going to use it with our probabilistic. We don't need any additional deterministic cases because we're going to derive them all from this base case. So let's go ahead and create our risk and sensitivity analysis. So it's risk model. We're going to link that to our base case. And now we have our inputs for the model shown here. Instead of specifying constant values for all of these as we would for a deterministic case, we're going to put ranges in for all of these input parameters. And that's what we do to do a probabilistic approach. For PI, we're going to leave it as constant. For XI, we're going to allow it to range in a uniform distribution. And the minimum one that we want to use is going to be that 100 feet. It's very unlikely that the fracture length is less than 100 feet because we did our linear flow analysis and showed that our transition out of linear flow occurs when the fracs are about 100 feet. So yes, the fracs, I mean, there are model combinations that could probably give us fractures that are less than 100 feet, but it's unlikely. It seems very likely that we have at least that much frac length. So we're going to use that as our minimum. For our maximum, as I said before, we're going to use 400. We've established that we can get a match at the maximum value. So at anything in between 100 and 400 we know is going to be reasonable, and we're going to want to investigate all of those values. LE we'll leave as a constant. FCD we're going to make an automatic parameter estimation. NF we're going to set up as a triangular distribution. Our minimum in this case is going to be the number of stages, which is 20. The mode is going to be 40, which is our 50% perf cluster efficiency. And the maximum is going to be 80, which assumes that every single one of the perf clusters is effective. Let's go to K1. We'll set that to APE. K2 is also going to be set to APE. XI is going to be set to APE. So these are all history matching parameters. The model for each one of its runs will calculate these values to get the best possible match. YE we're going to leave as a constant at 1200. There's not much sense in changing this value. We know what the well spacing is. We're going to leave that in place. Now for H, I'm going to set this one up as a triangular distribution as well. And we're going to make the mode 200. And we're going to go plus or minus 100 feet for minimum and maximum, just to give us a little bit of flexibility in what that frac height might end up being. For porosity, we're going to set that one up as a triangular distribution as well. Again, our mode is going to be 7, and our low side is going to be 4. Our high side is going to be 10. Gas saturation, water saturation we'll leave as is. For rock compressibility, we're going to set this up as a uniform distribution. For our minimum, we're going to use 0.5 e to the minus 5, which is consistent with the Hall correlation. 5 e to the minus 6 or 5 microsips is consistent with the Hall correlation. For maximum, we're going to allow it to go all the way up to 3 e to the minus 5. So we're going to let it go up to 30 microsips. That's a pretty good range for CF. Note, though, that for real cases where you do have some rock mechanics data, you want to use whatever laboratory data you have available to constrain this. In this particular example, I don't have any data, so I'm using a very wide range. Now, for PWF, in this case, I'm just going to assume the constant is 1,000. We're not going to assume any uncertainty in PWF. This is something that you may want to consider for probabilistic modeling, however, because operational uncertainty does factor very largely into the uncertainty in EUR. So if there's any uncertainty in what that long-term pressure constraint might be, we could definitely accommodate or want to accommodate that into our risk model as well. CGR, let's do something with CGR. So I'm going to make that a uniform distribution. We're going to say that the best possible case that we could have is that CGR stays at 270. That's our best case scenario. At the worst case scenario, that CGR could drop right off. So we're going to have that drop all the way down to 50 and allow it to explore a number of different solutions or a range of solutions in between 50 and 270. This will give us a more realistic or more cautious or conservative forecast or series of forecasts for condensate, where we're not just assuming that we're going to keep the yield at a constant value of 270. Gamma, we're going to set as an APE parameter, just as we have before. And now this is basically configured so that we can do our risk modeling, our probabilistic modeling. Before we get this thing started, we're going to want to run a validation case. Typically with a validation case, we don't want to do 100 runs. We're going to want to do just, say, 15 or 20 runs. Let's set that up to be 15. I probably do want to put an APE limit on here. That's an APE error limit. And so let me go back to my base case. I want the match to be of just as good quality as this, and that's 5%. So let's say, in order to be inclusive of all the history matches that are reasonable and exclusive of all the history matches that we don't think are reasonable, we'll set that average error to be about 7%. We normally go up a couple of percentage points just to be a little bit more flexible and let some of those solutions in. So let's make that maximum error 7%. I'll hit accept, and let's run the simulation. This will give us a sense for how many of the solutions are going to be acceptable and included in our risk portfolio. All right, so as we can see, we only got 3 successful cases out of the 15, so that's not a very good success rate. The results look fine in terms of the forecast, but the perhaps the error restriction we put on the model was too restrictive. So let's try running it again, and we'll make the error restriction a little more relaxed. I'm going to set that to be 15 instead of 7, and we'll run our full case this time. Let's run this 200 times. We'll run that simulation. All right, well, the simulation is coming to a close, and as you can see, we have about 54 out of 200 successful runs. That's not a great success rate. Normally, we would hope to get more successful runs than that. However, we can see the results look reasonable. What we might want to do, because of the low success rate, is choose a larger number of total runs with the aim of getting more successful runs. Sometimes we just have to run that many more to get the number of successful runs that we require. The distributions that we can see in production rate, in the forecast, rate versus QMAN, rate versus time, look reasonable. Let me expand these so we can look at them a little bit closer. That's our P90 forecast, P50 in the middle, and P10 on the outside. Rate versus QM plot, same sort of thing. We have our P90, P50, and P10. These are for gas. We're going to show the same information now for condensate. So let's take a look at rate versus time for condensate, and then in the top right hand plot, rate versus QM for condensate. So again, everything looks reasonable there. These are the gas, ultimate recoverable gas distribution and original gas in place. Let me show the distribution for condensate in the top left hand corner, and then we can review some of the results that way. So ultimate recoverable for condensate, there we go. So our P50 for condensate is 785,000 barrels. Our P90 is 680,000 barrels. For gas, we have a P50 of about 3 BCF, P90 of about 2.5 BCF. And you can see there's quite a lot of variation in our original gas in place, also because we put uncertainty in the volumetric parameters H and porosity. Let's investigate some other results that may be of interest. We want to also see what the distribution on permeability is. So we'll take a look at reservoir permeability. That's K2. That obviously has some interest. As we can see here, there's somewhat of a normal looking distribution. Again, to get this smoother, we'd probably want to do more runs. But we have a P50 right in the range of 50 nanodarcies. That's very consistent with what we know about the Eagle Ford. So that makes sense. Again, nothing in here too much higher than 100 nanodarcies. There was one case that gave a high permeability here of higher than, or a little bit higher than 100 nanodarcies. There wasn't anything higher than that. And we went down into some significantly low values for K2 as well. Another thing we might want to take a look at is the XF. Now, XF was an input here. If what we would expect to see is a uniform distribution. But what this might illustrate for us is some interesting things. Even though we started out with a uniform distribution, you can see the distribution shows that there were much higher acceptance rate on low fracture lengths than higher fracture lengths. And in fact, when we get up into the 300s, there was a very low frequency of acceptance. And so that would suggest that the frac length is probably, just based on investigating the allowable parameter space, the fracture length is probably somewhat lower. It's more likely that it's going to be in the range of 100 to 200 than, say, 200 to 300 or even beyond that. So the statistical results can give us a good indication based on the number of runs that we do on where the likely results would be, where they would lie in terms of fracture length, permeability. Another one that we can take a look at that I'll show in the bottom left-hand corner is our gamma factor, which also has some interest. So again, our gamma factor, this is related to geomechanical effects. Our P50 value for this is 2.4 e to the minus 4. There were some solutions that required a higher gamma factor, but it seems that the likelihood for gamma was closer to that minimum value that was specified in each of the models. So again, this gives us a sense for where some of the likelihood of some of the parameters may lie. Now we're going to go to our gas cum plot, and we're just going to view all of these probabilistic results on one single graph. Let's remove the base case, and we're going to keep the minimum on here just for comparison purposes. But what we'll also do is show our base case 90, our base case 50, and our base case P10. And so this gives you a sense for the overall range. Our minimum case kind of lies in the middle here somewhere, but with a lower EUR. P90 is sitting at around 2.5 BCF, P50 sitting at around 3.1 BCF, and P10 sitting at about 3.8 BCF. So that concludes the analytical portion of the workflow for the Eagle Ford Gas Condensate. There is another section, an additional video, in which we will discuss numerical modeling considerations for this gas condensate well. But that it completes the workflow for the analytical portion for this Eagle Ford Gas Condensate well.